Planck said that only certain values of energy are allowed, and you've got a distribution of oscillators right the way through the solid. So there aren't so many at the high frequency region, and there are more at the lower frequency, but dependent on the temperature. And his theory then matched the experiment in terms of black body radiation. Now, the second system I want to look at is the heat capacities. And I want you to remember that we did deal with the equipartition theorem. And just recall that if you've got atoms in a solid, the average energy of each of those atoms oscillating in the solid, because there are two quadratic terms contributing towards the energy, the average energy is 3 kT because it's in 3 dimensions. So a half kT from the potential energy due to springs, half from kinetic energy in each dimension times 3, and you'll end up with a total of 3 kT. Now, kT is like R, but for an atom, the gas constant, but for an atom. And so if you want to look for a total 1 mole of atoms, you just multiply this by Avogadro's, and of course, Avogadro times K gets us to R. And so the total internal energy, which is Avogadro's times the average per atom, the total internal energy is 3RT, which means that the change in internal energy per temperature, the change in internal energy per temperature is 3R. And that change in internal energy per temperature is simply the heat capacity. So this is quite an interesting result because it means that all solids have the same heat capacity, which I find I didn't quite expect. And of course, we know what R is. If you look up on the table of constants, we know that R is 8.314. And so 3 times 8 is 24. So the heat capacity of solids should be around about 24 joules per Kelvin per mole. And this matches experiment very well. Have a look. Cadmium, well, maybe it's slightly off. Copper is closer. Chromium, etc. Look at all these values. The heat capacity seems to match. And of course, maybe what's confusing is that this is a molar heat capacity, not a heat capacity per gram, for example. So you would need to take the densities into account if you wanted to get the heat capacity per gram. But of course, in terms of moles, they all match very well. So all of these substances have a heat capacity that's around about 24, which is around about 3R. Okay, so that's Dulong and Petit's law, is that the heat capacity is 3R. But of course, where is the problem then? Because we've got to see what the problem is with heat capacities. And the problem is that when you cool a substance down to really low temperatures, the heat capacity, yes, for high temperatures is 3R. So if you imagine this line is 3R, it's been scaled by 3R, so that's why there's a 1 there. But this line is 3R. But if you get the temperature to go lower and lower, you find that its heat capacity drops. And its heat capacity drops right down as you get to absolute zero. It drops right down to nothing. And so there's a problem. And that problem was solved initially by Einstein. Einstein said that, well, you can't have the atoms in a solid vibrating at any temperature. There are set energy levels for each atom, and in terms of distribution, that not all of them are going to have to absorb energy at the start, and so your heat capacity will be a lot low. You'll be able to raise the temperature a lot faster at lower temperatures, and this was the law that he came up with. And Debye is a little bit more involved. Debye is actually more accurate and more sophisticated than Einstein's, but both of them as you get both of them to higher temperatures, they all match the de Long Petit of the heat capacity of 3R. And so really they say that at low temperature, you've got a few oscillators active, so all that energy can go into raising that temperature. At high temperature, you've got to distribute that energy across a lot of different oscillators, and so it's going to take a lot more energy to raise the temperature in terms of heat capacity. Okay, so in terms of the assignment I'd asked you to do, I'd ask you to choose either blackbody radiation or heat capacities and to team up with 2 or 3 of you and to get a write-up of maybe about 2 pages maximum, and then please upload that to RE Connected. So there's a lot of information on the web. If you feel that you're in a vacuum of information, just drop me an email and say you're looking for something around, you're looking for a paper or some more information about a particular topic, and I'll see it, but you should be able to find a lot of information yourselves. Okay. Now these two were a big driving force historically in making the case for quantum mechanics. Both of these said that you have certain energy levels available to atoms. You can't just have any energy level available. You can't just have any energy available. You have to have these levels. And so they were a very strong driving force in pushing the field of quantum mechanics. But of course, we've looked at some examples. We've looked at the spectra of hydrogen. We had a look at our iodine prac, where you've got the vibrational energy levels. We've got evidence that convinces us, I'm sure in the class, that there is a good case for quantum mechanics. But there are a couple of other cases that I want to have a look at. And in quantum mechanics, there's this whole thing of particles as waves as particles, which also contributes to quantum mechanics. And so if you have a look, I'm going to deal with 2 things. One is electron diffraction, so these patterns made by electrons going through an opening. And I'll have a look at the photoelectric effect, is when light shines on a particular metal. And in this case, you've got electrons that act like waves. They produce diffraction much like waves do, like sound waves or water waves do. These particles of electrons have wave-like properties. And when we look at the photoelectric effect, we'll see, well, hang on, we've got these light rays coming in, and yet they're acting like particles. And so you can get it to the point where electrons, single electrons, are emitted from the metal from these waves that are coming in. Okay, so particles as waves. Just if you have a look here at this diagram here, this shows what happens when water waves hit a barrier. And you'll see there's a wall here and an opening, and the water waves hit this barrier, which is not small. It's fairly, it's not too large. It's a barrier that goes here, and you'll see that down the center you can see the waves have great intensity. But I wonder if you can see on your slides, if you can see these regions as you go out, where the water waves are destructively interfering with each other, and you can't see any waves down that line. You can't see any waves there. You can't see any waves here. And so there are regions where you see no waves at all. So over here, you'll see ripples coming towards you. Here you feel nothing. Here you feel ripples. Here you feel nothing, and ripples and so on. That's from wave diffractions through an aperture. So that's what happens with water. It happens with sound. It happens with waves that we are familiar with, but it also happens with electrons. And so this is what happens if you have a beam of electrons going through an aperture. You see exactly the same thing. You see the ripples there. You don't see it there. And so there's constructive and destructive interference, and you get a pattern that's built up like that. And if you have waves going through a double slit, you can get quite a nice uniform pattern coming through. And you'll find that the same thing happens with electrons. If you put electrons through a double slit, you will get these patterns. And here it is. Here's the actual result from having a beam of electrons going through a double slit. So these electrons have wave properties. They interfere. They're act not only like particles but as waves. And you'll be familiar from first year of a de Broglie relation, which relates the velocity of a particle to its wavelength. And you will remember that you've got lambda is h over mv. Now, a slight change I want to do in this course is I don't really want to deal with mv a lot of the time. M times v, mass times velocity, is the momentum of a particle. So wherever you see that I've got a p, that p really means mv. And so particles as waves, we can relate. If we've got the mass of a particle, we know the velocity, we therefore know its momentum, and therefore we know its wavelength. Okay, so that makes it nice. If you put everything in terms of momentum, then you can say, well, if you've got high momentum, you'll have a short wavelength. If you've got low momentum, you've got a long wavelength. Remember that momentum is dependent not only on the velocity of a particle, but on the mass of a particle. That P is dependent on both quantities for particles as waves. So if we go back to the previous slide, we could characterize those electrons if we knew their velocity and therefore their wavelength, and we'd be able to predict the patterns we would get from those electrons. Okay. So this is the first problem, is that particles show diffraction. They show properties of waves, not just as particles. And the reverse is true. We know that light shows diffraction. So we like to think of light as a wave, but this experiment, the photoelectric effect, showed exactly the opposite. And what we have in the photoelectric effect is you've got a container with a vacuum in there, and you apply a battery across it, you've got a nice potential across there. And of course, no current flows. Of course, if you shine light, maybe red light at the metal, nothing happens. You shine very bright red light at the metal, still nothing happens. And so there's something wrong with the red light. The red light is not emitting electrons, but you might shine blue light at it, a very dim blue light, and suddenly you get a whole lot of electrons being released and you see current flowing. So it's nothing to do with the intensity of light. The intensity of light has nothing to do with it. It's the color of a light hitting the metal. It's the frequency of a light that hits the metal that causes a current to flow or not. So electron ejection depends on frequency and not intensity. And there's an exact value of frequency that works for different metals. So the way it works is that you can use monochromatic light. So if you've got light of a particular wavelength and you vary the potential of a plate, you can determine the energy of the electrons that are emitted as a function of frequency. And so have a look at this graph here. So these are for three different elements. And so what happens is you'll see that at low frequencies, nothing happens for this first, so at low frequencies, nothing happens. But as soon as you hit this frequency, you start getting electrons ejected, and you see the energy increases of those electrons as the frequency goes up. And for the second element, nothing happens even at this frequency, but you hit that frequency, electrons start to be ejected. And of course, as the frequency goes up, the energy of electrons coming off also increases. So the only way to explain what's going on in this experiment is to view light as a particle, and that light brings in a certain amount of energy, that light comes in as a photon, and that photon brings with it a certain amount of energy, and that energy may be enough to eject an electron from the metal, or it might not be. The particles are called photons. Energy is E is equal to h nu. The photon, when the photon strikes the metal plate, its energy is transferred to an electron, and so that energy from the photon translates to a work function. That's the energy required to remove an electron from the metal, and any excess will be kinetic energy of that electron coming off. So if you're at a particular frequency, so if you're at this particular frequency, this value here is the excess kinetic energy required, the excess kinetic energy that we'll find in the electrons that are ejected. Okay. This next slide shows a diagram, which is what I really like. So if you can imagine that this here, this work function, this property of the metal that you're looking at, has a level, an energy level that's over there, that if the light coming in has too low a frequency, then the total energy of the light can't overcome the energy required to eject the electron. So nothing will happen. If your frequency of your light is less than your level, then of course no electron is going to be ejected by the photon. However, if your energy of your light is really high, much greater than what's required, then some of that energy will be taken into the work function, getting the electron off the metal, but the remainder will be the kinetic energy of the electron. And I hope you remember that kinetic energy is a half mv squared. And of course, in the photoelectric effect, remember that your mass that you're talking about is the mass of electron. And so this here is the equation for the photoelectric effect. And this equation only is relevant over here. In this case, if your energy is greater than the work function, then you've got an excess of kinetic energy. If your energy is less than the work function, then there's no point in even, because there's no electron that's going to be ejected. You would get a negative kinetic energy, which is impossible. So don't even try this equation if the electron can't be ejected. So have a look at the task I've got an RU connected. Task I've got an RU connected, I've given you a work function. And of course, that work function, I've given it to you in horrible energy units. So please translate it to correct energy units. I've given you lambda for light. So I haven't given you frequency. So you've got to do a little work, change from nanometers to meters to frequency to energy in joules. And then you will be able to, for the light, you'll be able to compare the energy in joules of a work function that you have translated, and the energy of a light. And of course, if the energy of light is greater, then of course we've got a system that works, and then the difference is energy of the electron. And therefore, you'll be able to calculate the velocity of the electron by simply, if you know what the total kinetic energy is here, and you know what the mass of an electron is, you should be able to calculate the velocity of that electron. Okay. So just to summarize the photoelectric effect, just make sure that the energy of the photon is above the energy of a work function. And then if so, then use the equation. The kinetic energy is just the difference between the two. And of course, you can then rearrange for half mv squared. Okay, so that is this set of slides really is to make a case, and I think I'm certainly convinced that quantum mechanics is necessary when you deal with atoms and molecules, when you deal with very small things. But I hope that in this whole set of slides, you're also convinced that quantum mechanics is absolutely necessary if we're trying to rationalize, and we're trying to see what's happening at a microscopic level. Are there any questions?
Prof, there's a question on the chat if you want to have a look.
Okay, let me try and get to the chat. Just hang a moment. Here we go. Okay. So what happens when the kinetic energy of the electrode ejected energy is 0? Okay, that is a very, very good question. So over here, so if I can just go to a graph to show you what's going on here. So what happens if it's 0? You're really at this point over here. And when so when they actually did the experiment, they varied the potential to see, and you'll find that if you slightly less than 0, you get nothing, and if you're slightly more than 0, you get something. To get to exactly 0 is quite problematic. You will not, if the potential of your plate that you've got is matching, is at that level, you'll be at a boundary where even the slightest perturbation, even the most infinitesimal change one way will cause you to see the electron, and the other way to cause you to not see the electron. So it's a very difficult place to be, to have that exact, to be at that exact frequency. So does that answer the question?
Yes, it does.
Okay, thank you. Okay, are there any other questions? Are you happy with what I want you to do in terms of failures of classical mechanics? So I'm looking for for just a write-up that tells us what exactly the the uh, phenomenon is. So it needs to be quite descriptive. So like with heat capacities, you need to say, well, what on earth is the heat capacity, etc. Why is it 3R, etc. And when you view it in a classical way, then you look at the problem with viewing it classically, and then how quantum mechanics solves the problem. The same for black body radiation. Okay. Right now, I'm not going to do a long lecture today. So what I really want to do now at this point, if there are no further questions, because I want to spend a long time on the next set of slides. I want to go very slowly through slides next week. So I'm not going to start. So in the remaining time that we've got here, I would like to just check if there are any problems with that prac. And I think there might have been. So let's just see if I can find WebMo. I can't find. I'll maybe just share my desktop. Can you see my desktop? Yeah. Were there problems with WebMo with the prac? Would there be some tasks that you would like me to do in front of you to help you proceed with the prac? Can I do a scan quickly? Would that help? So here I've got WebMo in front of me. Can you can someone just comment on the chat if you can see it or not?
Yeah, we can see
Okay,
it.
perfect. Okay, so I'm going to just quickly do a scan. And you'll remember from molecular mechanics that we had a look at the bond angle, for example. So it'd be interesting to look at water, for instance, and to see if we were to change the bond angle, how the energy would change. And so the way I would do that is always you look for your job manager. It'll be sometimes on the left, or if you're in the job manager, you can always go to the top and start a new job. And so I'm going to create a new job. Okay, and sometimes it takes a little while for that. And of course, if I want to deal with water, I'm just going to go directly to the periodic table and deal with water. And so my first click in the window is going to be an oxygen atom. And so now I'm almost good to go, because the cleanup will add hydrogens for me and get the geometry right. So I'll do the comprehensive cleanup, and I've got water. Okay. So if I want to do a scan with water, I'm going to go to the tools, adjust. And of course, for a bond, I've got to click 2 atoms. For an angle, I've got to have 3. For a dihedral, I've got to have 4. In this case, I'm interested in an angle, so I'm going to click 3 atoms. So there's the first atom. If it will work, adjust. There we go, first atom, and there's the second atom, and there's the third atom. So I have got an angle selected. And now, once you've selected the coordinate that you want to scan, you can then go back to adjust, and you can tell it to scan coordinate. and I would like to start scanning. Maybe let's try at 90 degrees. And so we'll start and see what the energy is with a 90-degree water, and I'll stop it at maybe 120 degrees. And then let's maybe, it doesn't matter how many steps, the more steps you've got, the more detail you've got, but of course then the run takes longer. I'm going to try 10 steps for that water, for that primary scan. Okay. And then of course when you're ready, when you've got the scan, you'll see this yellow, and the molecule is good to go for a scan. And I have found that the semi-empirical work that MOPAC does gets out some really nice scans. So I'm going to use MOPAC in this case. There we go. And I can then proceed. And I'm going to just, it's a coordinate scan. Make sure that it's a coordinate scan and PM6. And so then the scan will then proceed. So in the task I've given you, you've been asked to draw Li2. And so in that case, the scan is just a distance. So you would select just the two atoms, and then you then scan it, go back to the tools menu and adjust, and tell it to scan between 1 and 5 angstroms. So this is now complete. So of course, as in all cases, when your job is complete, go then to the view job. And of course, the results, if you're on a computer, the results are not immediately visible. You have to go down. If you're on a cell phone, there's a menu for the results. So you can go directly to that menu. But a computer, just remember to scroll down to find the results. So they're the parcel. So here's the coordinate scan. You can animate it. That's quite interesting to look at. But I'm just going to go to the magnifying glass to actually view the result. And so this here is a coordinate scan. And so we can see that the equilibrium, according to MOPAC, the equilibrium bond angle is about 101, maybe at about 102 degrees. It's not quite what we expect, but maybe because MOPAC is approximate quantum mechanics is what it's doing, and you can end up getting that. Of course, on the computer, you can save that image if you want to. If you're on a cell phone, just find a way to get an image of a screen once you've got this. Are there any questions? Is there anything else in terms of a prac that you may be struggling with? Okay. So please then, if there are no questions, even on the chat, if there are no questions in terms of either the slides or in terms of the prac itself, I'm always open to questions. So I have my email. So just be, I will respond to any emails that come my way. So please be in contact. And of course, if you post on the WhatsApp group as well, then your question can be seen by everyone else, and it may be helpful to other people as well. Okay, so if there are no further questions, then I'll call it a day, and then we will meet again on Monday at 11 o'clock. Okay, thank you.